So, a warm greeting to all of you. This is Tania from MSc Ed Physics. So, I'm going to discuss on the topic carbon nanotubes and nanofibers. So, coming to an introduction, nanotechnology deals with materials in the size range of 1 to 100 nanometers. Carbon based nanomaterials show unique mechanical, electrical, and thermal properties. So, in which we are going to study specifically about carbon nanotubes and carbon nanofibers. Carbon nanotubes are cylindrical structures formed from rolled graphene sheets, and carbon nanofibers are filament-like carbon structures with stacked graphene layers. So moving to carbon nanotubes. They are cylindrical nanostructures made of graphene sheets. The diameter is in nanometer range, length up to micrometers, and strong sp2 carbon-carbon bonding, and also they have extremely high aspect ratio. So coming to the types, there are mainly two types. First one is single walled carbon nanotube. It has one graphene cylinder and has high electrical conductivity. The second type is multi-walled carbon nanotube, in which it has multiple concentric graphene cylinders and it has a higher mechanical strength. The diagrams are given below. The right side diagram represents the single walled and the left side represents the multi-walled carbon nanotube. So moving to carbon nanofibers, these are fibrous carbon structures with stacked graphene layers, and it has a larger diameter than carbon nanotubes. And these are graphene layers arranged in parallel herringbone or cup stacked forms, and these are easier and cheaper to produce than carbon nanotubes. So moving to the properties, they have very high tensile strength and also excellent electrical conductivity and high thermal conductivity and also low density as well as high chemical stability. Now we are going to see some synthesis methods. There are mainly three methods. First one is chemical vapor deposition, second one is arc discharge method, and third one is laser ablation method. So moving on to the first synthesis method, which is the chemical vapor deposition method. It is the most widely used method for synthesizing carbon nanotubes and carbon nanofibers. In this technique, hydrocarbon gases such as methane or acetylene are passed over metal catalyst particles at higher temperatures, usually between 600 and 900 degrees Celsius. So the gas decomposes on the catalyst surface, releasing carbon atoms. These carbon atoms diffuse and arrange themselves into tubular or fibrous structures, forming CNTs or CNFs. So the CVD offers better control over diameter, length, and alignment and is suitable for large scale industrial production. So coming to the next method, which is arc discharge method. The arc discharge method is one of the earlier techniques used to synthesize carbon nanotubes. In this method, two graphite electrodes are placed close to each other in an inert gas atmosphere such as argon or helium. When a high electric current is passed, an intense arc is produced, generating extremely high temperatures. Due to this heat, carbon from the anode vaporizes and then condenses on the cathode in the form of carbon nanotubes. When metal catalysts like iron, cobalt, or nickel are added, single walled carbon nanotubes can also be produced. The features of this method is that the metal catalyst like iron, cobalt, nickel is used for the production, and it produces high quality crystalline carbon nanotubes, and it requires purification to remove amorphous carbon, and it is limited control over size and alignment. So moving to the last synthesis method, which is laser ablation method. So in this method, a high power laser beam is focused onto a graphite target containing metal catalyst particles. This process is carried out in a heated chamber filled with inert gas. The laser vaporizes carbon atoms from the target, and as the vapor cools, the carbon nanotubes are formed and deposited on a collector. This method produces highly pure and uniform single-walled carbon nanotubes. However, it is an expensive technique, consumes higher energy, and is not suitable for large-scale production. Coming to applications. Carbon nanotubes are widely used in nanoelectronics due to their excellent electrical conductivity and small size. They are used in transistors, conductive films, and interconnects. Because CNTs are highly sensitive to changes in their surroundings, they are also used in chemical and biological sensors. Even small changes in gas concentration or biomolecules can alter their electrical properties, making them ideal sensing materials. The second application is that carbon nanotubes and carbon nanofibers are commonly used as reinforcement materials in composites. When added to polymers, metals, or ceramics, they significantly improve mechanical strength, stiffness, and durability while keeping the material lightweight. Due to these properties, they are used in aerospace, automotive, and sporting goods industries to produce strong and lightweight components. Third one is in energy storage applications. CNTs and CNFs are used in lithium ion batteries, supercapacitors, and fuel cells. Their high surface area and excellent electrical conductivity improve charge storage and charge transfer efficiency. Carbon nanofibers are especially useful as electrode materials because they provide good electrical pathways and structural stability, enhancing the overall performance of energy storage devices. Also, in the biomedical field, carbon nanotubes are explored for drug delivery, tissue engineering, and biosensing. Their nanoscale size allows them to penetrate cells and deliver drugs directly to targeted areas. CNTs are also used in imaging and diagnostic applications due to their unique optical and electrical properties. However, their biocompatibility and safety must be carefully evaluated before clinical use. Carbon nanotubes and nanofibers are used in environmental applications such as water purification and air filtration. Their large surface area and porous structure enable them to absorb pollutants, heavy metals, and organic contaminants effectively. CNFs are also used as catalyst supports in environmental remediation processes. Due to their high electrical conductivity, CNTs and CNFs are used in electromagnetic interference shielding materials. They protect electronic devices from unwanted electromagnetic radiation. These materials are also used to develop anti-static coatings and flexible conductive materials for modern electronic applications. Coming to advantages and limitations. Carbon nanotubes and carbon nanofibers offer several important advantages. One of the main advantages is their extremely high mechanical strength and stiffness, which makes them ideal reinforcement materials in composites. They also possess excellent electrical and thermal conductivity, allowing their use in electronic devices and energy storage systems. In addition, these materials are lightweight, chemically stable, and resistant to corrosion. Their large surface area further enhances their performance in applications such as sensor, batteries, and filtration systems. Despite their remarkable properties, carbon nanotubes and nanofibers have certain limitations. The large scale production of high quality CNTs is still expensive and technically challenging. Uniform dispersion of these nanomaterials in composites is difficult, which can affect performance. There are also concerns related to health, safety, and environmental impact due to their nanoscale size. Furthermore, difficulties in controlling their structure, alignment, and purity limit their widespread commercial applications. So, in conclusion, carbon nanotubes and nanofibers are advanced carbon based nanomaterials that exhibit exceptional mechanical, electrical, and thermal properties. Their unique structure at the nanoscale makes them highly suitable for applications in electronics, energy storage, composites, biomedical engineering, and environmental protection. Although challenges such as high production cost, dispersion difficulties, and safety concerns still exist, continuous research and technological advancements are helping to overcome these limitations. With further development, carbon nanotubes and nanofibers are expected to play a vital role in future scientific and industrial applications. So here ends our presentation. I hope everyone is clear with the topic. Thank you.